So what we are going to do is we'll start and we'll first talk about the fundamentals. Then based on the fundamentals, we will solve some popular questions. Towards the end, we will top it up with a nice challenge. What is searching? If I ask you to define searching in your own little way, how would you go about it? You can just say you have a collection of items. Let's say you have some integers, for example. Yeah. And there is a target and you have to search that target. So here, if you search 4, you will get it here at this index. Let's say this index is I, you can return I and your job is done. The simplest way to search something is to start searching from the first position and keep going till you hit the last position. This is the idea of linear search, right? Yeah. So this is the idea of linear search where you start from the first index and go towards the end. Now, this is perfectly okay for a data which is random. What I mean by random data is that there is no order in the elements. Okay. But if there is some sort of order in elements, then the things become very easy. For example, if you have to find a word in dictionary, let's say you have an Oxford dictionary at your home and you want to find the meaning of a word, and let's say that word is monkey. How do you find that? Do you search this word monkey in a dictionary right from page 1 and then 2 and then 3? Do you go like that? No, that's the most foolish way, right? So how do you search something in dictionary? You pick a random page. So let's say you pick a random page and on that page you found a word which was stallion, right? Now this word stallion, we all know that will come at a page later than monkey, because in a dictionary, words are sorted alphabetically or lexicographically. And we all know that A, B, C, D, E, F, G, H, I, and M, N, O, P, Q, R, S. So M is smaller than S. So if this is some page where monkey is present, at a later page, stallion would have been present. So if on your current page you got stallion, you will definitely not want to look ahead. You would only want to look back, right? So this is the idea. The idea is that if you have some order, you can always discard a search space. You can always say that, hey, this search space is useless. My answer doesn't lie here, so I'll focus in this part. As simple as that. Okay. Now, with this idea, the binary search is created where we say that, hey, let's say we have an ordered array, and I am mindfully using the word ordered. Sorted is just a specialized version of ordered. Okay, and I'll show you some examples of it in time to come. Let's say you have an array which contains elements in sorted manner: 1, 5, 6, 9, 11, 17, 22. And let's say your target is 5. You want to search for 5. Okay. The idea behind binary search is you always start with the entire array and then you hit the middle element, right? And you compare that middle element with your target. And if that middle element is, let's say, greater than the target, then you know that everything in the right side will be even greater, right? So you now focus in the left side. Correct? But on the other hand, imagine your target was not 5. Imagine your target was 17. Then after hitting this middle element, you would have told yourself that, hey, everything behind 9 is smaller than 9. So I'll not waste my time there. I'll focus in the right side. So you can clearly see here that depending on whether your target is larger or your target was smaller, you are either switching to the left side or switching to the right side. Now, what that means is that initially, if your search space is of size n, after exactly one iteration, your search space becomes of size n by 2. If you go to the right side, then also it is n by 2. And if you go to the left side, then also it is n by 2. Now, this is amazing. Why this is amazing is because from a search space of size n, we are reducing it to half. And if we keep following the same rule, like let's say your target was actually 17, and now you said that I want to search in this part, right? Then what will you do? You will again find out the midpoint, and here luckily the midpoint contains value 17 and you will return this 17 and the job is done. Now, even if your target was not 17, if let's say you were searching for 20, you would say that, hey, this 20, if I consider this search space, 20 is greater than the midpoint. So I'll focus on the right part of it. So your search space is again half of the initial one. So your search space keeps on becoming half of what it was. And finally, it would become of size 1 and then even 0. If you're not able to find element, your search space would completely vanish. So here, if you take a look, how many steps would be there? So I can say after one step, the search space is of size n upon 2 power 1. After two steps, n upon 2 power 2. So let's say the number of steps were k. So after kth step, the value would be 1. Now from here, if you solve, you will get k equals to log n base 2. So it means that just after log n steps, we will be able to converge. We will be able to, uh, pinpoint to just one element and check it and say whether that is our answer or not. Right? So that's the basic idea behind binary search. So if you were to implement it, how do you go about it? You always say that, hey, I will initially have some array, let's say 1, 5, 6, 9, 12, 17, 22, 30, 35. And you say that we initially start with the entire array, and then we realize we should look in left, and then we realize we should look in the right part of that, and then we realize we should look in the left part of that. So every time what we do is we focus on a particular subarray. We focus on a particular subarray. A subarray can be denoted by a starting index and ending index. For exact same purpose, we track low and high. So we initially say that, hey, the entire array is our search space, where low is this and high is that. So we initialize low to 0 and high to n minus 1. And then you write your logic. So how does your binary search? So how many of you here have forgotten the code of implementing binary search? Or maybe you didn't write it previously, or you wrote but you forgot. So how many people like that here? Can we just have a yes? Okay, so I'm just going to write it and it'll quickly remind all of you and bring all of you on exact same page. So what we are going to say is, inside this while loop, we will do something. What will we do? We know that from low till high, let's say there was some array, and let's say this point was your low and this was your high. You want to check what element is at middle, so that you can decide whether your target lies in the right side or left side. So what you need to do is you need to compute mid, and it will be nothing but low plus high divided by 2. Now the first thing is that if your array of mid is exactly equal to your target, you will be super happy. You will say that, hey, I got what I wanted, right? And you will simply return this index. But on the other hand, if you realize that your middle element is smaller than target, so just imagine your target was 19, but your middle element was 7. What would you say in this case? You would say that, hey, my answer will definitely not lie in the left part, because in left part, the values will be further smaller than 7. So I should focus in the right part. If you want to focus in the right part, what should you change? Should you change your low or high? You must change your low. You should bring it just towards the right side of your current mid. So in this case, what you will do is you will just say, hey, let us change our low to mid plus 1. And what to do in the else case? What does the else case mean? Else case means that, let's say your target, instead of 19, it was 1. If you're searching for 1, and if your mid was 7, you would say that 1 would definitely lie in the left side. To go to the left side, you would not change your low. You would bring your high from here to here. So your high needs to be changed to mid minus 1. And that is exactly what we will do. So we will say in the else case, high equals to mid minus 1. That's it. Does it make sense? How many of you are clear with this part of the code, which I have written here. Now, what about the termination condition? What about the base case? So in the worst case scenario, what might end up happening is that the element was not present. So if the element was not present, in that case, you will be out of space. So just imagine, let me give you a quick example. Let's say you had an array, you had 5 here, and you had 9 here, and so on and on and on. All right. Let's say this was your low and this was your high. So it means this is your current search space. Okay. Now, let's say this low index is 4 and high index is 5. What will be your mid? Your mid will be 4 plus 5 by 2, which is 4. And let's say the target you were looking for was 10. Okay. Here, your midpoint is 4 and the element over here is 5. So what will you realize? You will realize that your target is greater. Because your target is greater, so you would look to the right side. Looking to the right side means you will change your low. So now you will change your low to mid plus 1. The moment you do that, your low will start pointing to this, and low also becomes 5, high also becomes 5. Now at this point of time, when you compute mid, it will again be 5. And you will realize that the value over here is smaller. If the value over here is smaller, you will end up saying that, hey, I must look to the right side. Looking to the right side means you would change your low. The moment you change your low, the value of low will become 6. Now, this is a case where low has become 6 and high is smaller than low. This particular situation, whenever it happens that the value of low has become greater than high, we need to break the loop. Why? Because this situation denotes that now we are out of search space. The search space is exhausted. Because a valid search space means, see, in a valid subarray, the value of starting index will always be smaller than equals to the ending index. If it ever happened that low overshot high, that means you are out of search space. So you will say while low is smaller than equal to high, you will keep on doing this thing. And in the end, you can return -1 to signify that there was no index where my target was found. Because if at all it was there, you must have returned it right from here. Okay, cool. So this was a very basic idea of binary search for all of us, right? Now, what we are going to do is we are going to just pick some problems where we will see that how modified versions of binary search can be applied to solve some real world problems, to solve some really useful problems. So one very well-known problem is where you have an array. It's a sorted array. Okay, it's a sorted array. And let's say it contains elements like 1, 1, 5, 5, 5, 6, 9, 9, 9, 9. Okay. And then you are given a target. So let's say your target is 5 and you have to find its first occurrence. First occurrence means what is the first index where it is coming. So what is the first index where 5 is coming? It is index number 2. So my output should be equal to 2. That's what we want. Tell me one thing. If I run this code to solve this problem, will it be all right? No. Why won't it be all right? It won't be all right because this code is written in a way that the moment it sees that your middle element is equal to target, it returns that index without even checking whether this middle index is actually the first occurrence or second occurrence or last occurrence or what occurrence. See, you can understand it quite clearly. If you, let's say, had an array, you had 1, 5, 5, 5, 5, 5, 5, 9, something like this. Here, the moment you perform first iteration of your for loop, when this loop runs for the first time, you will get a mid, and that mid could probably be something like this. And the moment you see this index is 5, you will return this index, but that is wrong because the first occurrence is not this index, it is rather this index. So what to do? How to handle this case? So it can be handled pretty easily. It can be handled pretty easily, but there is something important that I want to tell you here. Okay, so just focus on that part and that would be pretty useful. See, what I can say is that let's say you are looking for the first occurrence of any random element in a sorted array. In a sorted array, what happens is, let's say you are looking for x, then all the occurrences of x will be coming together because it's a sorted array, right? So they will all be coming together. And then here, maybe you would have some element y, which is greater than x, and here maybe some other element, let's say p, which is smaller than x. But all the occurrences of x will be coming together, right? So if it ever happens that your mid is pointing to something greater than x, definitely in that case, I would want to move left. And if my mid is pointing to something which is smaller than x, I would want to move right. So what I'm trying to say is that this condition and this condition will remain intact. They will not change. They will remain completely intact. Because if you are pointing to an element which is smaller, then of course you need to go right. And if you're pointing to larger, you need to move left. The problem arises when you are pointing here, 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 or here. So in that case, how to determine if you're pointing to the first occurrence or not? So there are multiple ways of handling this. One simple way to handle is just use your common sense and tell me, how can you for sure say that whatever index you are pointing to is actually the first occurrence? You can do that by immediately checking the previous index. So let's say this is your midpoint. You can check the value at mid minus 1. If the value at mid minus 1 is different, for sure this is the first occurrence. Okay. But on the other hand, let's say your mid was here. The moment you would have checked for mid minus 1, you would have realized that, hey, this is also x. So you can say with guarantee that this is not my answer. My answer is lying in the left side. So that is the entire idea. So how do I sum it up? The moment your a of mid is equal to x, if you realize that your a of mid is equal to x, at this point of time, immediately check the value at mid minus 1. So if the value at mid minus 1 is different, this index is your answer. And if that is not different, which is, let's say your mid was here and you found that mid minus 1 is also x, so you can guarantee yourself that this is not your answer lies behind. If your answer lies behind, you can switch to the left side of your search space. And how do you do that? You do that by changing high equals to mid minus 1. Does this point make sense? How many of you understand this idea? Yeah, of course, you can do it without this check also. In that case, you keep on saving the answer. There are multiple ways, but at the end of the day, they do just the same thing, right? This is one such ways to do that. In this case, only for sorted array, of course, yeah, that was the requirement. I told you, your input is sorted. Okay. So yeah, so I told you that this and this will remain same. I just have to work on this particular code snippet. So let me just bring it from here and write it over there, that if my current index is equal to target, in this case, I need to look at mid minus 1. Now, if I realize a of mid minus 1 is not equal to target, what should we do? We can immediately return m. That is what I told you. If a of mid minus 1 is different than this, and this thing is x, this thing is your target, then this is your answer. And what to do in the else case? So else case means that your answer lies left. So let's say this was your mid, and mid minus 1 was also x. That means first occurrence lies in left side. So you need to change your high so that you can switch to the left side. So in this case, you will do high equals to mid minus 1. As simple as that. Now there is one small edge case with this. What is that edge case? See, lower bound and upper bound, they all are implementations of binary search only. So it's good that you use them after understanding how to implement these things on your own. Because if in an interview such kind of question is asked to you, the interviewer will not allow you to use the inbuilt lower bound and upper bound function. They would want to check your binary search skills. So you'll have to write it. Yeah, so I was talking about what is the edge case over here. The edge case is yes, all of you are right. Excellent. So see, the moment you are doing mid minus 1 or mid plus 1, you have to be very worried about index out of bound issue. Because if mid is 0, 0 minus 1 will be negative. So how to handle that? So guys, again, it's a common sense thing. If a of 0 is equal to target, let's say you wanted to find the first occurrence of 4, and luck by chance 4 was at the first index itself. So this itself is your answer. There is no index behind it. So you can put a special check that, hey, if my m is 0, I will close my eyes and return 0. That's it. That's it. Job done. So this is the way in which you can easily find out the first occurrence in a sorted array. Is it making sense? How many of you clearly understood how to find out the first occurrence in a sorted array? If I change the question and ask you to find out the last occurrence, how would you then go about it? Okay, so last occurrence, let's say you had 5, 5, 6, 7, 7, 7, 7, 10, 11. Okay, and let's say your target is 7, whose last occurrence is needed. So what will be the answer? At what index the last occurrence of 7 is coming? 0, 1, 2, 3, 4, 5, 6. So output should be 6. Correct. So how will you solve this question? So here again, tell me, if you are pointing to an element which is smaller than the target, you will go to the right side. If you're pointing to an element which is greater than the target, you will go to the left side. So those two conditions will not change. Only when you are here, the condition will change. Now, how do you recognize if you are actually pointing to the last occurrence? So if you are actually at the last occurrence, you will realize that the element just after it is different. But if you are not at the last occurrence, maybe second last occurrence or third last occurrence or fourth last occurrence, you will realize that the element in front of it is also same, is also same, is also same. So all that you have to do here is, instead of checking for mid minus 1, which you were doing here, this time you will check for mid plus 1. Did you get it? How many of you got this clue? That you will check for mid plus 1? Yeah. Now, while you are checking for mid plus 1, again, you will have to exercise one caution. And what will that be? Index out of bound thing. See, if the last occurrence of 7 was at last index, let's say you had 7, 7, and again 7 here. So in that case, if your mid is here, you cannot do mid plus 1. You will again get index overflow, right? So what will you do in this case? In this case, you will put a special condition. So, I can modify this existing code itself. I can say that, hey, uh, to implement the last occurrence logic, I'll say that if a of mid plus 1, if a of mid plus 1 is not equal to target, I will return mid, as I told you. So let's say this was the last index, and after that you had 17. You would say that this is my answer, right? But if that is not the case, then you know your answer is in the right side. This time right side. To go to the right side, what do you change? Do you change your low or do you change your high? You change your low. And how do you change it? Low equals to mid plus 1. Yes. And how about the edge case? If mid is at the last index, and at that last index, the value was equal to target, then that itself is the last occurrence. So that's it. Using this logic in a sorted array, I can find first occurrence as well as last occurrence in log of n time. And that is great. That is the fastest way to do it, right? Now, this question is asked in interviews in a little indirect way. So your interviewer will tell you that, hey, you have a sorted array and you are given an element. So let's say the element is 10 and you have to tell me the frequency of that element. What is frequency? Frequency means how many times that element is coming. What is the frequency of 10 here? The frequency of 10 is 3. And can you calculate it pretty easily? The answer is yes, because all that you have to do is you have to find the last occurrence and first occurrence, and that's it. Because if this index is j and this index is I, what is this length? That is j minus I plus 1. That's it. That's really it. So you can find out the frequency of an element in log of n time. How? By first finding the first occurrence and last occurrence, which we know takes log of n time, right? Cool. Is everyone clear with this idea of how to find the first occurrence, last occurrence, and all that? So now what we'll do is we will switch. We'll switch a bit because I want to show you a little different variety of problems. A little different variety of problems where binary search is not directly used, but the very idea of binary search is used and it's so beautifully used. So this needs a lot of focus from your side. I hope I'll get it. Okay. So the question is, this time we have a family of strings. Family of strings containing zeros and ones. So they are binary strings basically. You understand? Okay. So in this family of strings, the first member, the very first member is zero. Okay. This is the first string. And then you have a second member, and then you will have a third member, and then you will have a fourth member, fifth member, and so on and on and on, right? Now, every member is born from the previous member. Third is born from second. Fourth is born from third. Fifth is born from fourth. Do you know, do you remember Fibonacci numbers? How many of you remember Fibonacci numbers? Tell me. In Fibonacci numbers, what happens? Every next number is born from the last two numbers. You say that 0, comma 1 are the first two Fibonacci number, and the next one is the summation of this and that. And then again, the next is summation of this and that. And then again, the next is summation of this and that. So you say that every Fibonacci number is born out of the previous two members. The same thing I am saying here, but here situation is little different because here we have strings. But all that I'm saying is that every string is born out of the previous string. Now how? So what we do is we look at the previous string and we replace, this is quite important, we replace every 0 by 0, 1, and we replace every 1 by 1, 0. That's what we do. So, okay, I'll show you through an example and then probably it'll make much more sense. See, it's quite simple. All that we do is, let's say we want to create the next string. Okay. We look at the first string and we replace all the zeros by 0, 1. And if there was any 1, we would have replaced that by 1, 0. So here there is a 0. So I'll replace that 0 by 0, 1. And thereby I'll end up getting this. So my next member is 0, 1. Yeah. So what I was saying was uh, every member is born out of previous member. And how do we do that? We replace every 0 by 0, 1 and every 1 by 1, 0. So in order to create the third member, we will again replace every 0 by 0, 1 and every 1 by 1, 0. So if we do that, it will become 0, 1, 1, 0. Fourth string. Can you write the fourth string? I want you guys to write it in the chat box. In order to create the fourth string, you need to look at third and you need to replace every 0 by 0, 1 and you need to replace every 1 by 1, 0. So let's just do it and see what you're getting. Yes, all of you are right. So this 0 will be replaced by 0, 1 and then this 1 will be replaced by 1, 0 and this 1 again will be replaced by 1, 0 and this 0 will be replaced by 0, 1. And the same thing, like you can generate the fifth one, sixth one, and so on and on. So all of you understand the generation logic, right? Now, what is the question? The question is, you are given two integers, n and k, and you have to determine the kth character of nth string. So you have to determine the kth character of nth string. And this k and n, they are one based index. I mean, we are not saying that our first string is s of 0. Our first string is s of 1. And our first index is also 1. So that is what I'm assuming. So let's take an example. Let's say the value of k is 3 and value of n is 4, what will be the output? What is the third character of fourth string? So if you look, fourth string is this. This is the first character, this is the second, and that is the third character. So my output should be 3. So I'm telling it again, my indexes are 1 based, okay? So that is just a convention that I'm abiding. This is first index, this is second index, this is third index. So my output should be 3 in this case, okay? So tell me, if you have to solve this question, what is the easiest, what is the most brute force kind of idea that comes to your mind? The brute force, the naive approach, what is it? Yeah, that is the simplest thing that we can do. We can go ahead and generate the nth string and we can return its kth character. Job done. But what is problem with this approach? Tell me. Of course, it will give you a TLE. It can also give you MLE, which is memory limit exceeded. Why I specifically talked about MLE also is because look at the size of the string. What is the size of first string? Let's write that down. 1, 2, 4, 8. Do you see it is rising exponentially? Power of 2, which is exponential, right? So what will be the size of nth string? Can you just guess the size of nth string? Yeah, it will be 2 raised to the power of n minus 1. That's right. Because 2 raised to power 1 minus 1 is 1. 2 raised to power 2 minus 1 is 2. So basically the size of nth string is 2 power n minus 1. That's huge. So if the value of n is around 100, I cannot store such a large string in my memory, in my RAM, right? My program will crash. And also I'll get TLE because I cannot perform so many iterations. Even if I write a program which performs so many iterations, lead code or any coding platform will say that, hey, time up, right? We cannot execute your code for more than 2 seconds or whatever it is. So we need to look for some patterns. We need to definitely look for some patterns and then we can go ahead. So yeah, what comes to your mind? Okay, so now let's focus here and try to understand. I would say, what is the root of every string? When I say root, I mean, where did it come from? Let's say you talk about fourth string. Where did it come from? Where did it originate from? It originated from 0. It originated from 0, which is the first string. Yeah, you can say it originated from third, but third originated from second and second originated from first. So everything originates from 0 only, right? That is the base, that is the root. And what I mean by that is that if I backtrack this thing, it will converge back to 0. What I mean by backtrack is that while creating a string, you are replacing 0 by 0, 1 and 1 by 1, 0. Now I'm telling you, while backtracking, you replace every 0, 1 by 0 and every 1, 0 by 1. Just do this thing and see what happens. So let's say you try to do this thing. You would say that, hey, I will replace this 0, 1 by 0, this 1, 0 by 1, this 1, 0 by 1, this 0, 1 by 0. What we are doing? Remind yourself, we are replacing every 0, 1 by 0 and every 1, 0 by 1. Why? Because that is how it came. That is how we framed the string. So we are just doing the reverse of it. Now again, we will replace every 0, 1 by 0, every 1, 0 by 1. Now again, this 0, 1 by 0. So no matter what string you take, if you backtrack, you will go back to the same 0. So what I mean by that is that any string that you take in this family is actually a representation of 0. Every string is a representation of 0. It came out from 0. Fifth string, sixth string, whatever it is a representation of 0, right? And now I want to show you one more thing. So I'll pick this string. What is it? 0, 1, 1, 0 and 1, 0, 0, 1, and I'll write it here. 0, 1, 1, 0, 1, 0, 0, 1. See, we all know that this string, it came from 0. It originated from 0, right? Now this particular 0, when it decomposed for the first time, it became 0, 1. And then it became something, and then that became something. So basically, if I look at it, the first half of it, the first half of it has come from 0. And the second half of it has come from 1. That is what happened, isn't it? Because this 0 then became 0, 1. This 1 became 1, 0. And now this 0, 1 is responsible for this part, because this 0 became 0, 1 and this 1 became 1, 0. And this 1, 0 is responsible for this part, because this 1 became 1, 0 and this 0 became 0, 1. So what I am trying to tell you is that this entire string is representing 0. But the left half of it is representing 0 and right half of it is representing 1. If you just take the right half, just take out this substring from here. Just take it out and write it here. And if you decompose it, you will get 1. Just do it. Replace 1, 0 by 1, 0, 1 by 0, 1, 0 by 1, and this is what you get. So what I mean by that is, if there is any string, nth string, it's a huge, huge string. The entire string is representing 0. But the left half of it is representing 0 and right half of it is representing 1. Right? Now this decomposition is recursively true. And see, it is recursively true here also. I told you that this string 1001 is representing 1. And we all know that 1, when it would have broken as 1, 0. So I can say for sure that the left half of it is 1 and right half of it is 0. And that is true. You just look at the left half. 1, 0. If you backtrack, it will go back to 1. 0, 1. If you backtrack, it will go back to 0. So what I am trying to say from here is, if you take a big string, a big substring, which represents 1, then the left half of it would be representing 1 and right half of it would be representing 0. But if you take a big string which represents 0, then the left half of it will represent 0 and right half of it will represent 1. This decomposition is recursively true. Why it is recursively true? Because that is how we are generating the strings. That is the rule that we are following while generating the strings. Is it making sense? How many of you are understanding this thing? For a moment, let's say you generate your fifth string. Okay. Fifth string will generate from here, right? What will it be? It will be 0, 1, 1, 0, 1, 0, 0, 1, 1, 0, 1, 0, and then 0, 1. And then if you go on doing it, it will be 1, 0, 0, 1, 0, 1, 1, 0. That is what it will be. This entire thing is representing 0. But the left half of it, the left half alone will be representing 0 and the right half alone will be representing 1. Just try that. Okay, just try that. If you take this left half alone and you backtrack, you will say 0, 1 came from 0, 1, 0 came from 1, 1, 0 came from 1, 0, 1 came from 0. Now again, if you backtrack this, you will say this 0, 1 came from 0, 1, 0 came from 1, and this 0, 1 came from 0. So do you see the point that I'm trying to make? That this thing is nothing, but it is an expanded version of small 0. Do you relate? Yes or no? Now, for a moment, look at this right part and you yourself backtrack it. The way I have backtracked on this, you yourself backtrack this and tell me what you are getting. What do you get at the last? Do you get a 0 or do you get a 1? Tell me. You'll get a 1. You will get a 1. Let's do it. 1 0 will be replaced by 1, 0 1 will be replaced by 0, then again 0 1 will be replaced by 0, and 1 0 will be replaced by 1. Then again here 1 0 by 1 and 0 1 by 0, and this 1 0 by 1. And what I am trying to tell you is that this is not a stroke of luck. This is not a random thought. This is purely logical. Why this is purely logical? Because we know that this thing is built from 0. How it was built? There was a 0 at the beginning of the universe, which split as 0 1, which split as something else, something else, something else. So this 0, the left half of it, would be responsible for the left half of it. And this one, the right half of it, would be responsible for the right half of it. Can you connect the dots now? How many of you can clearly connect it now? And now what I'm saying is that this definition is recursively true. I mean, it's always true. I mean, it doesn't have anything to do with your knowledge of recursion. I mean, it's just a random statement. The important thing is that this statement is universally true. It's globally true. So what I will say is that if now I just pick this thing out from here and write it like this, write it like 0, 1, 1, 0, 1, 0, 0, 1. What is this representing? Tell me. What is this representing? This is representing a 0. So the left half of it would be representing 0 and right half of it will be representing 1. And you can try that out. This will decompose to 0 and this will decompose to 1. But on the other hand, if I pick this little thing and write it here, 1 0 0 1 0 1 1 0, what is this representing? This is the right half. What is this representing? It is representing 1. So what will the left half of this denote? The left half of this will denote 1 and right half of this will denote 0. Again, not stroke, it's not a stroke of luck. We know that there might have been a 1 at some time in the universe, and this 1 would have broken as 1 0, and then this 1 would have become this, and this 0 would have become that. So that's the idea. Yeah, it all starts from zeros and ones. And that's how this entire family is created. If you use this beautiful idea, you will be able to solve this question pretty easily without even generating the string. Without even generating the string. And let me tell you how. Let's say somebody told you that, hey, tell me the, what do you want? Tell me the sixth character of fourth string. So what we will do is, just for our convenience, we will write the fourth string. How did it look like, fourth string? Fourth string was this one, right? 0 1 1 0 1 0 0 1. 0 1 1 0 1 0 0 1. So somebody wants to know the sixth character. Now keep looking at it very carefully. Can you tell me what will be the size of fourth string? The size of fourth string will be 2 power 4 minus 1, which is 8. Correct? What will be the first index? The first index is 1 and last index is 8. So I will say that, hey, there is a string which is from index 1 to index 8. And this string, is representing a 0 because it is S of 4, right? Any string of the family represents a 0. Everything came from 0. Now what I'll do is I'll find out a midpoint of it. What will be the midpoint of it? 1 plus 8, 9, 9 by 2 is going to be 4. So if you look at it, the left half of it will be from 1 to 4 and right half of it will be from 5 to 8. So the left half of it will be from 1 to 4 and right half will be from 5 to 8. Which character you want? Sixth character. Given that you want sixth character, will you go to the left half or will you go to the right half? You'll go to the right half because right half contains indices from 5 to 8. You are interested in sixth character, right? And this is only, the left half is only index 1 to 4. So you will go to the right half. Now tell me one thing. If you're going to the right half of 0 string, what does that right half represent? Does it represent a 0 or does it represent a 1? It represents a 1. Very good. Now again, you will find out the midpoint of 5 to 8. This is 5, this is 8. What is the midpoint? 5 plus 8 by 2. How much is this? 6. So you would say the left half of it is from 5 to 6. The right half of it is from 7 to 8. Which half will you go at? If you need sixth character, will you go to the left half or the right half? You will go to the left half. Yes, very good. You will go to the left half. Now, when you go to the left half, given that your original string was 1, what will its left half represent? 1 or 0? The left half will represent 1. Very good. Now again, here, you will find out the midpoint. What will be the midpoint? 5 plus 6 by 2, which is 11 by 2, that is 5. So we'll say that the left half is from 5 to 5. The right half is from 6 to 6. Which half will you go to? Left or right? You will again go to the right half. Okay. Now, if you go to the right half of a string which represents 1, then what does it represent? It represents 0. Can this be our base case, our termination condition? Yes, this can definitely be our termination condition. Because here we reached that sixth character. We literally reached that sixth character and we are saying that the sixth character is 0. And let's check. 1, 2, 3, 4, 5, 6. Is it 0? Yes, it is 0. And we found that out without generating this string based on the idea of pattern. This is not exactly binary search, but this is very much like binary search. The inspiration, the idea of breaking into half, following the pattern, it all came from binary search. Did it make sense? So this is just one example. There are so many examples like this on binary search. Okay. So yeah, for beginners, it might have been a little challenging or something like that, but trust me, I mean, it's super easy to, follow once you are in rhythm or something. Okay. So yeah, let's quickly write the code for this. The code will be super easy. So you want kth character of nth string, right? Let's set our low and high. Yeah, I'll share the link of question with you. Don't worry about that. What will be low? 1. What will be high? 2 raised to the power n minus 1. Correct? Yeah. Now, what will be your logic? See, how do you work? Every time you find out the mid and you either go to right or you go to left. You either go to right or you go to left after finding your mid. That's what you do, right? Okay. And when do you stop? You stop when both the low and high are same. Correct? That is your base case. So you say while low and high are not equal, as long as low and high are not equal, what I'll do is I'll find mid, which is low plus high by 2. And now what I'll say is that my left half range is from low to mid, right? And right half range is from mid plus 1 to high. That is the case. So now what I'll do is I'll check if the value of k is smaller than equal to mid, I'll go to the left half. And in the else case, I'll go to the right half. That is the idea. Okay. So when you go to the left half, what do? Going to the left half means you want to change your high to become equal to mid. So in this case, you will do high equals to mid. And when you go to right half, you change your low equals to mid plus 1, right? Why low equals to 1? Because initially we are considering the entire string whose first index is 1 and last index is the length of the string, which is 2 power n minus 1. That is the reason. You got it? Okay, so this is how our high and low are changing. This is how we are either going to the left side or right side. Should something else also change? Yes. the current representation. So initially the current representation is 0. I mean, initially the entire string is representing 0. Now we have realized that if the current string is 0, and if we are going left, it remains 0. If we are going right, it becomes 1. But if the current representation is 1, if the current representation is 1, if we go left, it is 1. If we go right, it becomes 0. So there is a solid evidence from here that if you go left, the representation remains same. And if you go right, the representation toggles. Toggle means if 0, it becomes 1. If 1, it becomes 0. So what I'll say is that, hey, if I am going left, I'll not change my current. And if I'm going right, in one line, I can change it. I can say current equals to 1 minus current. See, automatically, if it is 0, 1 minus 0 will become 1. And if it is 1, 1 minus 1 will become 0. Finally, when this loop is over, low and high would have become equal. At that point of time, I can return current and the job would be done. What will be the time complexity? So what had we learned? This kind of algorithm where you are breaking your search space into half, 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 half every time. What is the basic idea behind it? What is your initial search space? So a lot of people answer log n. And unfortunately, that's not right. You need to go a little slow. What is the initial size of your search space? Tell me. From 1 to 2 power n minus 1, how long this is? The length of this is almost 2 power n, right? So initial distance between low and high is 2 power n. And then you divide by 2, so it becomes 2 power n minus 1. Then you divide by 2, it becomes 2 power n minus 2. Finally, it becomes 2 power 0, which is 1 where you terminate. So how many steps are there? They are not log n steps. The number of steps is n. Your answer is log of 2 power n. Because mind it, the distance between low and high is not n. The distance between low and high is 2 power n. So you know what people do is people mug up this idea that if it is binary says it is always log n. No. If it is binary says it is log of the distance between low and high. And what was the distance between low and high? It was 2 power n over here. Okay. Okay, some of you asked how current is changing. You didn't get it. See, the initial string is representing 0. And if some string is representing 0, then 0 splits as 0, 1. So if you go right, you have to change it to 1. And if you go left, you have to change it to 0. That is what I showed here. But if the substring that you are considering is, let's say, representing 1, then how does 1 split? 1 splits as 1, 0. So if you go to the left of 1, it splits as 1. And if you go to the right of 1, it splits as 0. That is the idea. So what I showed is that if you're going to the left half, your current is not changing. If you're going to the right half, it is toggling. From 0, it becomes 1. From 1, it becomes 0. Got it? Yeah, so the time complexity is order n, and it is way, 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 way better than our brute force complexity, which was 2 power n. There is no extra space. We are not using any sort of extra space over here.